Good afternoon to everybody. I'm Fabio Gerbino, responsible for calculation department of vehicle dynamics in Maserati. As many people know, at the end of the 2K19, we complete and inaugurate our innovation lab, Maserati Innovation Lab. In these facilities, we are developed our new cars, and we performed a lot of cutting edge in terms of technological point of view activities, and we have the possibility to make these activities with our simulators department. In Innovation Lab, we have from September of 2019 the DIM 250, but also from 2K14 we have also a static simulator and the compact simulator for HMI activities. Next slide, please. The DIM 250 is in charge to vehicle dynamics department, and the main activities that we follow are practically listed by this slide. We perform handling and comfort activities, but we are very focused also in tires development, and we have the possibility to increase the fidelity and the complexity of the model using our hills. In terms of complexity, the hills are, for example, have low complexity, for example, how the hill of the shock absorber, a medium high complexity of a steering hill test bench, and an high and advanced hardware in the loop bench test, as you can see in the below figure of the slide, the connection of the DIM 250 with our physical dyno test bench in two different facilities, farthest one between another by 10 kilometers. We have the possibility in this way to simulate, to replicate the real behavior of the engine with the connection to the DIM. Next slide, please. But at the moment, as we know, the development of the cars become more and more challenging and more shorter. And at the same time, we have the necessity to develop the cars in a timing shorter as possible, and at the same time our management requires target higher, as higher as possible. For example, in the previous approach we developed a car in 3.5 years. Now we have to develop a car in time lower than 2 years. For this reason, the only way to increase the fidelity of the development is the only way is to have a higher number of virtual tests. In the past, we perform 20% of the physical of the deliberate process of our cars in virtual way. Now we have to increase this percentage up to 70%. Next slide, please. And for this reason, we have to develop our cars as much as possible in virtual way. Here we can see a typical approach of virtual vehicle dynamics. Here we define 100% the suspension kinematic behavior and the secondary ride in terms of bushing stiffness. But also we have the necessity of the tires, the primary ride in terms of spring dampers and anti-roll bars, and of course the very crucial point in terms of vehicle dynamics development is the tires development. In the last years, we have to increase the knowledge of our virtual development, working together to tire manufacturer and advanced laboratory in terms of tires engineering like MegaRide. Next slide, please. In fact, a typical approach that we follow in this study is to increase the fidelity of the tires in terms of virtual development in order to amplify the range that we want to investigate. We know that MegaRide is able to provide to us a tool that permits to have not a standard MF tire, but an MF tire that takes into account the thermal behavior of the tires. For this reason, we develop our vehicle target setting process coming from the benchmark. We define a quality profile score in terms of SAA scale scores, and after that we deploy the target to the tires, not only in terms of classic vehicle dynamics point of view, of course, side slip angle, progression, understeer grind, and so on. But we want to give to our partner very challenging targets in terms of thermal behavior of the tires and wear and degradation. For this reason, we work together to MegaRide in order to develop a virtual workflow that takes into account also MegaRide tools. Please, Flavio.
Okay, thank you, Fabio. Just a few words about MegaRide project. So we are a startup company. We were born about 4 years ago as a spin-off company of the Vehicle Dynamic Group of University Federico II. We mainly develop technologies and models for the analysis and the optimization of vehicle performance with particular reference to tire physical modeling. And such technologies were awarded as Tire Technology of the Year at Tire Technology Expo 2018 and as Development Tool of the Year at the Vehicle Dynamics International Award in 2019. The significant applications realized in partnership with the relevant automotive companies and motorsport teams allowed to our team revenues to grow fast and to go on increasing in team resources and in revenues income. As concerns the interaction with Maserati, we met for the first time at Maserati Live Innovation Startup Program in Modena a few years ago. After that, we started with our research project and with the PhD path that we co-developed in Naples and in Modena. Thanks to the support of the Tire Lab at university, we have the possibility to have the facility that allows to carry out experimental activities to physically feed the physical models we develop. Let's go a bit deeper in what we want to present today. We all know how complex is facing tires, modeling, and characterizations. And I think a nice quote by Henry Louis Mencken says that for every complex problem, there's a solution that is clear, simple, and wrong. In our modeling approach, tires and vehicles need to be analyzed and integrated, accounting for the mutually interacting physical phenomena that arise at road contact. So our main target is in this way analyzing, understanding, and reproducing the complexity of tire multiphysical phenomena by means of a multiphysical platform that can enhance the level of reliability of vehicle simulations and of the driving simulation experience, of course. In the last years, we developed several physical modules now that cooperate in a modular platform that allows a holistic view of tire behavior, interacting with experimental data and models in the loop hardware, in the model in the loop, hardware in the loop, and driver in the loop context. In this way, we are able to go on board of driving of the DIM, the DIM model at Maserati Live Innovation Lab, in order to have a modular platform that we have called in this way and we launched today as RadSuit. RadSuit is a multi-physical platform that has inside several different modules and several different physical models, because it has at the right advanced Pacheco model that we choose because Pacheco model is very used in the automotive sector and is really compliant to many structures, is very compliant to hard real-time applications on which we work. Inside it has also a physical wear energy-based module that is called WearRide. Inside it has also a thermal model that is called ThermoRide, And finally, we have a multi-contact footprint module that allows to enhance the level of the reliability of the local contact forces that arise at the interaction between the virtual tires and the virtual road during a physical simulation driving experience. Of course, each model can work as a desktop offline tool, as a logic inside the max performance logics, and as a real-time solution in driver in the loop sessions. Now we can go a bit deeper inside what we are going to present you today. So the roadmap of the project we carried out together has, at the first stage, the parameterization of the target vehicle. After that, we tested the tires at University of Naples Tire Lab in order to parameterize the data, the tires. After that, we performed the outdoor testing session. And after that, we calibrated physical model in order to implement them on board of the Maserati Innovation Lab. First step was the development, the selection of the vehicle. It was a Maserati prototype vehicle. It's a real wheel drive vehicle. At the first stage, we had the target to parameterize from the physical point of view all the data that concerned with the vehicle itself, and that allowed to our physical instrument to analyze properly the performance of the tire and of the vehicle itself for the next stage. Second phase was the parameterization of the thermal model. At our lab, we have the possibility to have the facility that allows us to characterize tires in 3 different ways. From the footprint point of view, because of course footprints are fundamental in order to understand the exchange of energies that the tire and the vehicle exchange with the external environment. The second step is concerning the structural behavior, and so the analysis and the estimation of the strain energy loss phenomena due to the theoretical behavior of the viscoelasticity of the thread layer and of the carcass dissipations. And after that, we have the possibility to parameterize properly the thermal diffusivity and contact and the specific heat of each different layer that constitutes the tire, because of course we have the necessity to know with very high precision which ones are the thermodynamic parameters of each different material that constitutes the tire, because of course it's a multiphysical platform and it needs to be deeply known in order to understand everything. We have developed in the last year this physical thermal model that has up to 6 different layers in radial direction, up to 15 different ribs along the radial direction, because we work a lot also with motorcycles, and of course with the high inclination angle, it's fundamental to have this information. And all this stuff works and runs in real time, because it works both as an analysis tool and a real-time model that works on real-time simulators. After that, finally, the choice of the reference track, we went to Nardò, and we worked together with Nardò Technical Center in order to develop some specific maneuvers and routines that allowed to exert in the widest possible working range conditions the tire, because we wanted to analyze the pure interaction, both longitudinal and lateral, after that the combined, but all of that at different thermal ranges, because of course, basing on thermal approach, we need to know what concerns the interaction of the vehicle with the ground at different layers, because we want to model the physical reality in the widest possible thermal range. After that, we properly instrumented the vehicle, so with the CAN bus reader, with inertial platform, with optical side slip sensor, but in particular with very specific thermal equipment that allowed us to get information on the inflation chamber state, inner liner and external surface with local infrared sensors. After that, I leave the virtual microphone to Fabio.
Okay, thank you, Flavio. Now we can switch in order to this slide in order to see the results of the cooperation between MegaRide and Maserati in order to develop a multiphysics tire models that involve the project previous cycle. As you can see in this slide, we see that in experimental way, for the classic graph of vehicle dynamics, we see that, of course, as we know, the tire behavior change the vehicle dynamics performances, change the balance between front and rear axle, and also change the grip and the maximum lateral acceleration. If we use a standard Passeca model, a standard MF tire model, or a standard tire that not taking into account the thermal effect, we have not the possibility to cover the wide range, because we have to choose we have the possibility or to fix the best achievable performance on the optimal range, or to take into account the cold or the hot behavior of the tire. Instead, with the multiphysics tires, with the multiphysics tires model, we have the possibility to cover all the range in optimal, in cold, and in hot thermal condition. As we can see, with the thermo off, we have a reference in terms of slope of the axle. With the thermo off, we have a reference. Instead, with the cold tire, we have an increment of 62%, and with hot tires, a decrement of the corner stiffness about the 40%. So the variation for this type of tires is quite big, and with these models, we have the possibility to run in all the configuration, in all the thermal configuration. Next slide, please, Flavio. Okay, this is an interesting point of view in terms of objective maneuvers, because as we can see, the slow ramp steer and the frequency response, the random steering input, excite in different way the tires, because practically the frequency response don't change the thermodynamic behavior of the tires. Instead, the slow ramp steer permits to have a ramp up of the temperature on the surface, but also a little bit also on the core. This is the reason why we see all these a big modification on of the car balance on the slow ramp steer, on the understeering gradient graph. Next slide, please, Flavio. Okay. For this, also we have with MegaRide the possibility to look forward to other features that we want to add to our multiphysics tires approach. And for this reason, we work together to MegaRide in a PhD program in order to estimate with a few parameters live, but also in post-process, the relaxation length of the tires, in order to estimate as better as possible the delay of the front and the delay of the rear axles. Please, and practically at the end of the objective data analysis, we can see that we don't have a big variation in terms of frequency response, in terms of transfer function of the vehicle, and this is explained by the previous slide, when we can see that the thermal the maneuvers don't stress, don't excite the thermal range of the tires, don't change so much the thermodynamic status of the tires. At the end of this discussion, we made the final calibration of the tires in order to have a real-time model that is able to run on the track. Here we can see the validation of the thermodynamic status of the tires, taking into account the data coming from the experimental session that we followed together with Flavio, and Flavio explained it before. Here we can see the good correlation in terms of surface, but also in terms of inner status of the tires, and this is a good point of view in terms of correlation, because if we have a good validation of the external behavior, but also of the internal, we can replicate as better as possible the pressure variation, and also we have an high fidelity of the changing of the thermodynamic status of the tires and of the handling performance of the vehicle. At the end of this study, we can see, of course, the results. Here we can see also the grip graph versus temperature, when we can locus the optimal grip range, and also a very good correlation in terms of comparison between simulated lateral grip with respect to experimental one. At the end of this activity, we test these models with the virtual tires on our driving simulator in order to add a very important information for Maserati point of view for development of the car, the driver feedback. Because if we have to match, we have to close the circle with our drivers feedback, and we saw that with this multiphysics approach, the driver is able to understand the level of grip of the tires. The changing starts from cold to becoming hot, the condition of the tires. Instead, with thermo-off condition, we have practically we aligned practically the performance to the best optimal range, but we cannot see the decay of the tires, and the driver perceive very good the decay of the tires due to thermal behavior, especially on the rear when we see the snap oversteer during power on condition. Please, Flavio, I leave the word to you.
Okay, thank you. So now I can start the video. I hope you see it well. In this video, we reported the results of a run that has been performed with the DIM on the virtual Fiorano track. After that, the model were properly calibrated and validated. On the top left of the section, we see the front left tire, in which each different layer changes in real time its temperature due to the interaction with the external environment and with the adjacent layers. In the bottom of the plot, we see the 4 tires that move and change their colors with reference to the inclination angle and the steering angle and temperature. We think that the most important point regarding the constant availability of the tread core and tire carcass temperature that cannot be measurable outdoor and in normal situations is that they are deeply correlated with the grip and stiffness phenomena that can be reproduced by the HydRide model and that Fabio showed in the previous slides. In the last plots in the bottom, we can see the differences between the lateral forces reproduced by HydRide and the ones coming from a standard Pacheca. And it allows to highlight again how the tire is a multi-physical system and has to be treated in this way in order to optimize its own performance. Sorry, okay. Then finally, in this last slide, we can see what happened when we simulated 3 different warm-up laps. We started with very cold tires, and after 3 laps, more or less the average temperature of the tread core and tread base layer went more or less close to the optimal working range temperature. In this way, we were able to study the optimization of the warm-up phase. And of course, as you can also see from the data that come from the lap times or the minimum and the maximum longitudinal and lateral acceleration, we were able to understand which starting conditions, which vehicle setup, and which tire setup conditions allowed us to performance and optimize the tire performance from the global view that relates to tire global behavior. Of course, all this stuff in this case have been studied related to a brand new fresh tire, but we are able to get also inside the model all the variability linked to wear and degradation phenomena, and that in this way affect all these phenomena, as we saw last week with the webinar that we had with MegaRide online. After that, we would like to thank a lot Maserati for its cooperation, and all the young guys from our research group and working group that worked a lot in these last days to perform proper simulations and to allow us to be here with a presentation we hope you liked. Thank you.